Hey everyone, this is Eric Griffin here from Positive Energy in Austin, Texas. I'm going to talk to you a little bit about how to know you got a quality manual J today. Hopefully we won't get off too far into the weeds and we'll move on through what you need to know, but we are going to start off with a little bit of background information. Now, Positive Energy, we're an integrated design building science company here in Austin. We consult for uh, HVAC design, building enclosure design, and any kind of indoor air quality issue that may come about. So, what are our learning objectives for today? Well, first off, we're going to be basically defining all the different terms that you would find in your Manual J report: BTU, sensible heat, latent heat, tonnage, airflow, and what to expect from the loads and what the different types of loads are on the house. Second one, we're going to figure out what's important. Things that the owner, the contractor, and the installers need to understand and what it means. And thirdly, how to use it. The basic do's and don'ts for selecting equipment based on your Manual J. We're not going to get too far in that because it gets very complicated with all the different types of equipment out there, but we'll kind of cover the basics. So, let's talk a little bit about heat. BTU is a British thermal unit. I don't know why exactly we're using it, but it's like you can think of it as like a kitchen match. It's enough heat to raise 1 pound of water 1 degree Fahrenheit, and it describes a quantity of heat. That's important to remember. So a BTU's quantity per hour equals BTUH. Normally, you would think that you would see it BTU over hour, but I don't know, somewhere along the line, somebody got lazy and decided to write it all on one line. So BTUH, BTUs per hour. Don't get confused by it. It's fairly straightforward. And that describes a rate because it's per hour. And one thing to keep in mind, I always like saying this, is there's no such thing as cold. There's only heat and lack of heat. Cold simply means there is less heat. So, getting a little bit further into it, let's talk about sensible heat. Sensible heat, you've heard of dry bulb. That's essentially what we're talking about, sensible heat. It gets transferred through the three different types of heat transfer: convection, conduction, and radiation. It does not include moisture. So you can actually think of it a little bit as convection is the heat rising inside or outside of the wall. Conduction is what is going through the wall. And the radiation largely is through windows. It can be just any kind of any surface temperature that is hotter than your body will radiate towards you. It is line of sight and at the speed of light and will travel through the vacuum of space. That's how the sun's heat gets to Earth, is by radiation. It's pretty incredible force, but probably actually the weakest of all of these ones that we're talking about so far. One thing to remember is this dry bulb does not include moisture and humidity. So what does, of course? Well, latent heat does. It literally means hidden heat. And in the southeast part of the country, you always hear it's not the heat, it's the humidity, and that's very true in a lot of aspects. But it relates to the amount of water vapor in the air, and it's largely driven by infiltration and ventilation, to the order of 10 times more than you would get through like vapor drive through an assembly. So let's talk a little bit about sensible heat ratio. It is the sensible heat divided by the total heat. And as you can probably imagine, the sensible plus latent equals the total. So that's where that comes from. And the typical values for it are somewhere between 75 and 77%. Those are usually what's used in load calculation software and as standard industry rules of thumb and typical values. But always know that they will vary, and it's very hard to quantify it because it's constantly going to be changing depending on how much humidity there is in the air. Now, where this comes in handy and what you will typically see is if you have a 3-ton air conditioning unit, 36,000 BTUs, tons are measured, 12,000 BTUs per ton. If you have a 3-ton air handler with a SHR, the initials for sensible heat ratio of 75%, that will give you 27,000 BTUs of sensible heat capacity. That's fairly straightforward math right there. So tons, where does that name come from? Well, it's a concept that came from the amount of heat it takes to melt 1 ton of ice in 24 hours. So if you have the this heat capacity of ice, 143 BTUs per pound, times 2,000 pounds a ton, you get 286,000 BTUs. Divide that by 24 hours, and like most everything we do in the air conditioning world, we like to round to nice even numbers to work with, and that's roughly 12,000 BTUs per hour, and that is where ton comes from. Now, a little bit about airflow. Where does it come from? How does it get calculated? The units are selected based on the sensible heat gain of the building. And what you would expect from your airflow is your quantity of sensible heat equals 1.08 times your CFM times your change in temperature over the air conditioning coil. So the number 1.08 comes from the heat capacity of air times 60 minutes per hour. And if you've ever heard of kind of the typical rule of thumb, CFM per ton, 400 CFM per ton, you can look back to this formula and kind of see where it came from and why it exists. So if you use the formula we talked about, the quantity of sensible heat equals 1.08 times the cubic feet per minute of air times the change in temperature across the coil. And let's assume you've got a sensible heat ratio of 75%. You've got, for that same 3-ton unit we were talking about before, if you've got 27,000 BTUs, and that will equal 1.08 times cubic feet per minute times typical temperature change across a coil is going to be about 20 degrees Fahrenheit. That is a typical value. Then you end up moving all of the numbers around and solving for CFM, and you end up getting somewhere close to 1227 CFM for this system. Now remember, it was a 3-ton system, so that's going to give us somewhere right around that 400 CFM per ton. It's kind of funny how that works out and how you are starting to see the trend of rounding happen. Okay, so what we've got here now is a submittal for a certain piece of equipment. And as you can see up here at the top, it's got the total cooling capacity of 12,300. So that is going to be a 1-ton unit. Down here at the bottom, you see that the high airflow rate, the high is 360 CFM. And you would expect to see something like that because it is a 1-ton unit and it's close to 400 CFM. In this circle right over here, now these are AHRI testing conditions. where your indoor temperatures are set at a particular level. They've got the 80-degree dry bulb and the 67-degree wet bulb, and the 95-degree dry bulb outside condition. That's for your air conditioning conditions, and that's going to be standard across the industry. You should see that everywhere. What you should know about those test conditions is your summer design temperatures are probably going to be different than what they're doing this testing at to establish the cooling capacity. So, like for instance, if you want to have a 75-degree summer set point inside of your home, you would expect to probably have a little bit less cooling capacity with this unit because it wasn't tested. It was only tested for an indoor condition at 80 degrees. So it's going to have to work harder to make your home cooler. And your outdoor temperatures may be different. Here in Austin, it's 100 degrees, so we would expect to get a little bit less air conditioning out of this unit than that 1 ton, just because the air that it's trying to exchange heat with outside during the summer is hotter than the 95 degrees that it was tested at. One thing that I also like to pay attention to, draw your attention to, is the external static pressure of the units. Now, this is really important when you start talking about duct systems. Keep in mind some of the newer equipment out there has very low static pressure tolerances. And so like on this system with a 0.1 inch water column static pressure limit, you aren't going to be able to put very much ducting on it. This is not probably a good option for replacing most indoor air handler units unless you have one single duct running out of the top of your unit. Then maybe it'll be able to handle it. But a very low number like this basically means that the system's not going to be able to tolerate much ducting, and that you need to be careful with the duct design. Now, normal values for this are going to be somewhere in the 0.5 inches of water column range, and some units max out around the 0.8 inches of water column. Much beyond that, you're not going to get the airflow. For instance, on this one, 0.1 inches of water column, if I were to put this on a duct system that had a few too long duct runs off it, I would expect to get on the high setting much less than 360, probably closer to just 300 even on the high setting if my ducts weren't designed appropriately and if there were too many ducts on this system. So here we got another submittal for a different piece of equipment. This is a 3-ton piece of equipment. You can see that right there, 36,000 divided by 12,000 equals 3. And so this is a 3-ton unit. And, you know, what you would expect to see, exactly what we're looking at down here. You've got the 365 CFM per ton, which is what we'd expect to see. And then, of course, the circles again. This actually proclaims that it's the AHRI standard here. You can see those right there. That is the generally accepted testing standard for all air conditioning equipment. So you should see that somewhere and not be surprised by it. But just know that those temperatures are probably different than the temperatures of your application. So you would expect to see different cooling capacities coming out of your unit. And again, the external static pressure. This is one of the units that has 3 different settings. 0.3, 0.5, and 0.8 inches of water column. 0.3 would be a very efficient, well-designed, well-installed air duct system. The 0.5 would be right in the mid-range, typical homes, maybe not a typical home system. What is the typical home? But the 0.8 would be a very large duct system, possibly a small, poorly installed system, maybe with a lot of flex duct that's not well installed. And those limits are going to have a lot of effect on the performance of the fan that's trying to push that 400 CFM per ton, or this 365 CFM per ton in this case. So now let's talk a little bit about design conditions, and we'll start talking about the different types of load conditions. So what we're looking at here is a graph of the Austin bin weather data. It shows the different outside dry bulb temperatures throughout the year and the number of hours per year that we would expect to see those temperatures. So the bin weather data, that comes from the TMY3 data. That's the typical meteorological year data. This is data that is collected from weather stations all over the United States for different locations, actually all over the world for different locations, and it is a 30-year running average. So it's, as you can see, I mean, in Austin, about 4 or 5 years ago, there were 10 days in a row of 110 plus degree temperatures. Those don't show up because those temperatures don't show up often enough to alter the 30-year running average, which is where this data comes from. So the summer temperature here in Austin, our design temperature, is 100 degrees Fahrenheit dry bulb. This is actually set by our local code officials. It's really close to what ASHRAE's Handbook of Fundamentals suggests we use, which is the 1% dry bulb. In Austin, if you looked it up in ASHRAE, it would be 99, but our code official, I don't know what exactly his reasoning is, but he allows one extra degree. But as long as your design temperatures are, within reason of what you would expect, if I were to see a summer design temperature of 98, 99, 101 or so, I might give somebody a hard time, but wouldn't raise too much of a stink because they're going to be close enough. And if you look at these numbers and kind of think about them a little bit, somewhere between 60 and 70 degrees is really close to half of the year that no heating or cooling is needed in any substantial way. And so you can imagine that actually a little bit beyond 50% of our typical year, you wouldn't necessarily need heating and cooling. And that starts to describe a little bit of what we like to call part load. Now, moving same information, this is just moved to a different graph. What you've got over on the left-hand axis is hours, and then you have across the horizontal axis, you have the months of the year. So as you can see, we've got the blue line with winter hours. So as you can see, the red line is summer hours. The green is in between hours, what I'm referring to as in between. And what you can see here is, as you would expect, in January, we have no summer hours, anything above 78 degrees Fahrenheit. It gets pretty close sometimes, but virtually nothing there. And all of the hours of January are below 68 degrees, so we need heating then. During the summer, we get some really hot temperatures, a lot of hours that we're going to need cooling. Anything above 78 is there in July. We can see it peaks out somewhere. That's going to be around 580 hours per year. And then the green line really kind of shows you the kind of moderate temperatures around the year. And as you can see, we have a significant amount of swing season hours during March, April, May, into June. September and October it can be very mild. And those are times when you don't necessarily need heating or air conditioning, and that's when we start talking a little bit about part load. But this is what I was talking to. This was in 2011. This, if you look up into the right set of ASHRAE data, you can see this is our 50-year extreme design temperature. So once every 50 years or so, we should expect to see temperatures near 112 degrees Fahrenheit. They should not happen very often at all. Like I said before, not enough to alter the TMY3 running average data, but occasionally we can hit that. And this would be for the extreme load. And if somebody ever wants you to design an air conditioning, or if you're thinking that you want to be able to cover the hottest temperature it'll ever get in your climate, well, if you think about it, that's going to be a very poor way to cover the more moderate times of the year. If you design for a house in Austin for an outdoor design temperature of 112, well, we virtually never get there, really. So you're sizing a system, and it's going to be way oversized for normal operation. It would just be bad practice. So what we've got here is a report that you'd see out of a popular. So what we're looking at here is a common report out of a popular Manual J software. This gives you a lot of different information. It can look a little bit overwhelming at the beginning, but it's fairly straightforward, and you want to kind of just take it all in, look at what all the numbers mean, not get too overwhelmed, but let's look at the ones that are really important. The ones that are most important are, starting with from the top corner, the outside dry bulbs. You would expect to see values in Austin for the heating value of 30 degrees and the cooling temperature of 100 degrees Fahrenheit. As long as you're within a degree or two of your climate and what ASHRAE would suggest for your 1% dry bulb temperature, that's a reasonable value and would be considered close enough. The 75 degree temperature right here for your inside dry bulb is an important number also. You want to make sure that typical value is 75 degrees. Sometimes you can see it moved up. You rarely will see it moved down. I think Passive House Standard has it up to 78 degrees. If you saw anything up to 80, or if you saw anything down below 75, you might raise an eyebrow, because that's going to have a direct effect on the size of your unit. If that number goes up towards 80, you're going to have a smaller air conditioner. If you move that number down to 72 or 70, you're going to have a much bigger air conditioning unit, and it's going to get the unit that you'll have to specify to cover the load will get bigger faster as that number goes down. It won't move significantly, or won't move as much if that temperature goes up, but it will move some. And then construction quality. The typical house that are being built to, let's say, for instance, the 2009 code that's adopted in most places now, if not beyond that, are pretty good houses. Air tightness, construction quality wise, that's what that's referring to, is the air tightness of the building. 7 ACH 50, 5 ACH 50 here in Austin. That's not all that bad. And so you would want to see a value that's no worse than what you would consider average. I think tight or semi-tight would be a possible way to go. This is going to have a significant effect on the size of the unit as well. So you don't really ever want to see anything that's worse than average, because if it's worse than average, you would have a tendency to oversize your unit. Now, down here's the area column, and when we're looking at the area column, we just want to make sure that everything's within plus or minus 10% of somebody else's calculation. Typically, the architect or a builder will give you a square footage number, and different trades, different professions are going to measure from different parts of the walls. Different areas are going to, different locales are going to measure from different corners of the building and so forth. So as long as you're within plus or minus 10%, that's a reasonable figure. The closer the better, but don't get too crazy trying to figure out who measured what wrong. As long as you're within 10%, you're good to go. The cooling load, this is the important part. The sum of these numbers is how you pick your unit. This is largely talking about the sensible load on the equipment. Down at the bottom, you'll see the latent load. That's 1,874 BTUs per hour of latent load on this particular house. But that's not the most important number. The most important number is just the sensible number, which is going to be right here. You see that entire house number right there, and you can cover the equipment loads with it as well. But that's the number that you're going to look to size the equipment. And of course, if you go back through these calculations that I showed you earlier, using these the sensible numbers and converting it to figuring out how many CFM, you're going to end up getting really close to this 505 CFM that they've auto-calculated for you. So this is another example of a software report. This is a load preview report of another popular Manual J software. There's lots of information on here, nothing too overwhelming because you're starting to get familiar with this and what to expect. We've got the most important column right here, which is the sensible gain column. That is the column that you're going to use to select your air conditioning system for your house. That is absolutely the most important column. And if you do some calculations, you'll see where they came up with the CFM over here, because we know how to do that now. The building, if you take this net ton calculation, it's just that. If you see the net gain, divide that number by 12,000 and you get that number, 6.99. That is the total sum for all of the building, not just the individual zones or the systems that are there. Down here you can see another, this has ducts that are in unconditioned space. So there's going to be a certain amount of latent gain. These are probably in an attic or a crawl space. And then you can see the net tons are listed right here. And once again, the square footage per ton, which is an interesting number. You can see right here, we've got two different values. This one is going to be 520 square foot per ton. The one up above is 1,780 square feet per ton. So you can see they're going to be different values for different houses. So if somebody's coming up and suggesting that they do 400 square feet per ton, and that's the way that they size the units, and that's the way that they always have, go find somebody else, because they're going to be leading you in the wrong direction. You can't do that. Houses are so much different than the rules of thumb, the way that they dry and the way that they perform. New houses can't be done that way. We see houses in our practice that can range anywhere between 300 square feet per ton all the way up to 1,000 square feet per ton. It's not uncommon for us to hit 1,100 square feet per ton, and one of these days we'll get beyond that into the 1,200 or 1,300 square feet per ton mark when somebody wants to do a passive house or something along the lines of that, some really intense energy efficiency standard. So rules of thumb with sizing units don't necessarily work. Okay, I just explained a lot of what the different parts of this are. What do I really need to pay attention to? Well, it's this sensible gain portion of the puzzle. You want to make sure that the unit that you have is able to cover this sensible gain. Don't worry about the latent gain. Don't worry about net gain. Air conditioning, speaking of air conditioning, you want to make sure that this sensible gain gets covered. That's the most important part. And remember that good inputs equal good outcomes. The better information that you give to your designer, the more accurate information he's going to be able to put into the model, the better this load calculation comes out, the more accurate it is, the better you're going to be able to choose the right piece of equipment for your house. Good inputs equal good outcomes. Summing it up right now, a better model yields better results. The better information that you can get to your designer, the more accurate your manual J is going to end up getting. He's going to need information about your window values, your overhangs, the orientation, how you're planning on insulating the different building assemblies of your house, how tight you expect the house to be. So each one of those is going to have a significant impact on the outcome of your manual J. Remember, when you're picking units, you really only want to go to look at the sensible heat gain of the house. That is going to be the most important value there. The latent will be taken care of by the air conditioning running as long as you size the house correctly. The sensible is the most important piece of the puzzle. So make sure the sensible capacity of your unit is sized appropriately and closely to the sensible load of your house. Remember also that part load dominates the number of hours per year. If you remember the charts that were earlier, roughly half of the hours in Austin per year typically are in the zone where you don't necessarily need heating or air conditioning. So remember that when you're picking your unit, you want to have something that sizes pretty close to what the load calculation is giving you. Anything much beyond that is going to be overkill and is going to be running in poor fashion for the majority of the year. And you can easily have indoor air quality issues because you won't have you won't have enough air movement, you won't be properly dehumidifying your space. There are just lots of negative impacts of oversizing because part load dominates the year. To cover this further, oversizing is problematic. You really want to make sure that sensible capacity of the unit is close to the sensible capacity of your load, or excuse me, the sensible load on the house. You rarely hear any complaints about undersized units. It's more often that you hear problems with oversizing. We have builders out here in Austin that we work with regularly that will go out to the houses that they've built in the middle of the summer on the hottest days and check out to see if their air conditioners are running 100% of an hour. And they should be. That's how you know you've sized your unit right. There's a reason why it's done that way, is because that's the most efficient. It helps save you on your first cost, and it helps you save on your utility bills throughout the lifespan of the equipment in your house. And the other thing, we really didn't cover this too much, but it's important. The manual J will actually tell you how to distribute the air throughout the house. Each one of the loads will give you, each one of the loads, which you should be getting on a room by room basis, will tell you how many BTUs of heat you need to be able to offset with your air conditioning. And now with the formulas that you've got and what you should see on the different reports, you should feel comfortable in trusting the manual J to get the appropriate amount of CFM to each one of the rooms. So good luck. If there's any other questions or anything that we can do, feel free to reach out to us and for any kind of clarification. We are Positive Energy, and we're here to help.